Hey friends, Dr. Boroli is here. Today we are learning a PN junction diode. PN junction diode is a semiconductor device. So let us understand something about semiconductors. Semiconductor is material having conductivity between conductors and insulator. That's why it is called as semiconductor. The popular semiconductor materials are silicon and germanium. Those can be used for electronic device making. Silicon is quite popular compared to germanium because germanium is much more temperature dependent performance. Gallium arsenide can also be used for high speed semiconductor device manufacturing. The semiconductor devices are nowadays mostly made using silicon and gallium arsenide. Semiconductors are broadly classified in two groups, that is as intrinsic semiconductor and extrinsic semiconductor. Intrinsic semiconductor is a pure semiconductor, and extrinsic semiconductor is a semiconductor in which the pure semiconductor is getting doped with the impurity purposeful so that the properties of the semiconductor can be modified. Intrinsic semiconductor, also called pure semiconductor, by definition, the semiconductor with the impurity level less than 0.01 ppm is called intrinsic one. Semiconductor have a crystalline structure. Typically, if we take a silicon, it consists of four valence electrons in the outer shell. And therefore, to have a stable outer shell, we need at least 8 electrons in the shell. Therefore, these atoms makes a covalent bond with the adjacent atoms of the material, and that form a lattice structure. The lattice structure exists from 0 degree Kelvin onward. Here it is shown in the figure. At 0 degree Kelvin, that is minus 273 degrees centigrade, each silicon atom is tied in the covalent bond with the adjacent four atoms and now sharing the total 8 number of electrons, 4 of its own and 4 from the neighboring atoms, and get stable. The covalent bonds are the bonds which are keeping the material atoms in immobile position. Now, what will happen if the temperature is increased? That we will see. When temperature is 0 degree Kelvin, all the electrons in the bonds are tied with each other and there is no free electron available at 0 degree Kelvin. And therefore, there is no electron available in the conduction band of the semiconductor at 0 degree Kelvin. And therefore, pure semiconductor is having no conductivity at 0 degree Kelvin, that is at minus 273 degrees centigrade, and it behaves like an insulator. At room temperature, say at 25 degrees centigrade, or thermal energy is supplied. Due to this thermal energy, some of the covalent bonds are broken. This happens because when the thermal energy is supplied to the material, the electrons from valence band will jump to the higher level, and that is the conduction band. If sufficient energy is injected in the material, they can cross the energy gap of the material from valence band to conduction band. And then these electrons are available for conduction under the application of external field. Therefore, at room temperature, we will find that some of the conduction band electron constitute to the conductivity of the semiconductor material. The pure form of the semiconductor is not suitable to make the devices because its conductivity is low. Here the figure is showing the generation of free electron hole pairs when the thermal energy is applied. We can recall from the Bohr's atomic theory and the material structure that atoms are firmly and mechanically tied in the crystalline structure and they are not moving in the material. And whenever one of the electrons is removed from the atom, it leaves behind the positive charge ion in the material as immobile ion. It is having positive charge in the form of hole in the valence band and it remains immobile. Whereas the removed electrons, due to the supplied external energy, if that energy is sufficient, it will be shifted to conduction band as shown and available as a free charge carrier. So whenever one electron is removed from the atom, it generates two particles. One is the free electrons in the conduction band and a positive charge tendency called hole in the valence band. These two particles, that is hole and electron, takes part in the conduction if external field is applied across the semiconductor. Let us see the process of conduction in pure semiconductor. Here in the figure, when no external field is applied to the semiconductor and if we are operating at room temperature, some of the electron hole pairs are generated due to the thermal energy supplied. So at room temperature, some of electron hole pair exist in the semiconductor and here in this figure, the free electrons and hole pairs are shown with the broken covalent bond. Since no external field is applied, these free electrons and holes are randomly moving in the material and thus the average motion of the particle is zero and therefore average current flowing through the material is zero. When we apply a specific potential as shown in this figure 2, right end is positive and left end is negative for the material. Then, due to this applied electric field, the electrons are moved under the electric field created force. So, electrons are attracted towards the positive terminal of the external source, and holes are moved towards the negative end of the external source. And therefore, the current is established in the semiconductor specimen. So, in summary, whenever the electric field is applied across the semiconductor, there is a directional motion of the particle which constitute the current in the pure semiconductor under the force created by the external electric field. This motion of the electron is called as drift motion, and the current under the influence of applied external field is called as drift current. The total current flowing through the semiconductor device is now sum of the two currents. One is because of the electrons and another is because of the holes moving in the valence band. The pure semiconductor is doped so that its properties can be modified and make suitable for making the devices. So we can define the extrinsic semiconductor as a semiconductor with added impurity via a process called doping. Impurity is nothing but the other material. Doping is a process of adding the impurity in the intrinsic semiconductor. The effect of doping on the conductivity can be analyzed on the following points. Due to doping, the conductivity of the semiconductor increases. Thus, in the extrinsic semiconductor, better conductivity results than the intrinsic semiconductor. Thermally, increased conductivity is not very useful for making the devices. Hence, the conductivity increase by means of doping process is the major charge carrier generation process in the semiconductor. The extrinsic semiconductor are extensively used in manufacturing of all electronic components such as diode and transistors. The extrinsic semiconductors are further classified in two groups as N-type semiconductors and P-type semiconductors. The creation of the P-type or N-type semiconductor depends on a type of impurity which is added. If the type of impurity called dopant is trivalent, then P-type semiconductor is generated. If the dopant is pentavalent type, then it donates one extra electrons and therefore more number of electrons gets generated in the semiconductor material and N type of semiconductor results. The donor impurity is a pentavalent impurity and acceptor impurity is trivalent impurity. If the impurity atom is a pentavalent atom, then pentavalent atom consists of 5 electrons in its last orbit. So whenever they form the covalent bond with the semiconductor atoms, 4 out of these 5 electrons are engaged in the covalent bonds with the semiconductor material. And 1 electrons from the covalent bond remains loosely bound with the nucleus, and with slight energy it will jump to the conduction band and easily available for the conduction. So it will donate 1 electron per impurity atom. And thus, if there is say 10 raised to 5 impurity atoms in around 10 raised to 20 pure semiconductor atoms, then around 10 raised to 5 conduction band electrons are generated and available for the conduction at room temperature. Since pentavalent impurity donates 1 electron, it is also called as donor impurity. And since it is giving the new negative particles, that is electrons for conduction, the semiconductor which is doped with this impurity is with excess number of electrons and therefore can be recognized as N type of semiconductor. If the impurity is an acceptor impurity, that is trivalent impurity, these impurity material atoms have 3 electrons in its valence orbit, and therefore there is always deficit of 1 electrons. Whenever this atom forms the covalent bonds with the neighboring silicon atoms, there is deficiency of 1 electron in the covalent bond. Means there is a strong tendency of attracting 1 electron in the covalent bond, and this strong center tendency of attraction is called holes in the valence band. So, one acceptor atom addition gives rise to 1 hole in the valence band in the doped semiconductor. So, if you take the example again, in 10 raised to 20 silicon atom, if 10 raised to 5 impurity atoms are added, then the specimen consists of at least 10 raised to 5 holes created and available for free conduction. Here, we are ignoring the thermally generated hole electron pairs. Whereas when the semiconductor is operated at room temperature, the particles are generated, maybe electrons and holes. Those are because of the impurities added as well as the thermally generated electron hole pairs. Thermally generated electron hole pairs are less compared to the impurity generated electron hole pairs, and therefore thermally generated particles are also contributes to minority charge carriers in the semiconductor. In making N type of semiconductor, the antimony, arsenic and phosphorus can be used as a pentavalent impurities. Here the figure shows the doped semiconductor in which the center atom here shown is of arsenic and other atoms in the structure forming the covalent bonds with this arsenic atom. Here arsenic atom have 5 electrons in the valence orbit. So 4 out of these 5 are tied in the covalent bonds with the neighboring silicon atoms. And 1 electron is loosely tied with the nucleus that is available for conduction in the conduction band if slight thermal energy is applied to it. And therefore, per impurity atom, we got 1 electrons donated to the pool of electrons for conduction. Whereas in this structure, if we repeat the example of 10 raised to 20 atoms of silicon and 10 raised to 5 atoms of impurity atom, in N type of semiconductor now, there are 10 raised to 5 free electrons available. Whereas due to temperature, if some of the covalent bonds are broken, say 100 number of covalent bonds are broken, then there are 100 holes and 100 electrons are generated additionally due to breaking of these covalent bonds. These extra 100 electrons are added to the donor generated electrons. That becomes 10 raised to 5 plus 100 number of electrons. And the specimen also consists of the free holes. Those are 100. So we observe that in the doped semiconductor now there is majority of electrons and very few amount of holes. So in N type of semiconductor, therefore, holes are considered to be minority charge carriers. Similarly, whenever we use a trivalent impurity, we get huge amount of holes for conduction and very few amount of electrons in P type of semiconductor. And therefore, in P type of material, the electrons are minority charge carriers and holes are majority charge carriers. You have to remember the concept of majority charge carriers and minority charge carriers in the extrinsic semiconductor. Now let us see the conduction in extrinsic semiconductor. Now whenever we are applying the external potential, the current flows because the charge particles are moved in a specific direction and constitute the current. We have seen that the current is flowing because of two particles, holes as well as electrons. The total current is the summation of electron current and hole current. This current is because of the application of external potential and therefore particles are moved by force and therefore they are drifted and therefore the current constituted is called as drift current. Let us see the example of N type of semiconductor. In figure 1, we will show a N type of semiconductor with the silicon atoms as well as impurity atoms. And here the electrons are shown by the black dots, whereas holes are shown by the hollow circle. You will observe that the electrons are more in the specimen and holes are less because in N type of semiconductor, the majority charge carriers are holes and minority charge carriers are electrons. When we apply the potential across the specimen as shown, left side end is positive and right side end of the specimen is negative, then electrons are drifted towards the positive terminal and holes are drifted towards the negative terminal. Since more amount of electrons are there, the electronic current will be more and the hole current will be lesser. Here you observe that the silicon ions, those are not moving because they are tied in the covalent bonds. And therefore in the second figure, only the free charge particles are shown. There always exist the immobile ions in the material, which constitute the material structure. But since they are not movable, therefore they are not shown in the simplified figure. The conventional current that is coming out of the specimen is because of the current due to electrons as well as current due to hole. Now, if you see the P type of semiconductor now, the doping impurity is a trivalent impurity, also called as acceptor impurity. Typical material used for making P-type semiconductor are boron, gallium, and indium. Here, the structure created after doping is shown. Here, one impurity atom of gallium is shown. It forms the covalent bonds with the neighboring silicon atom in the extrinsic semiconductor. Since gallium have only 3 valence electron, they form the covalent bonds with the adjacent atom, whereas one covalent bond is still have a deficiency of 1 electrons. This deficiency is indicated here by the strong center of attraction for electron, that is hole. And therefore, per impurity atom, we have one hole generated. And at room temperature, some of the covalent bonds are broken that generates the additional electron hole pair. Those are the minority. Since in the P type of semiconductor, when doped with trivalent impurity, we have huge amount of holes present in the valence band for conduction compared to the electrons, and therefore holes are majority. Now let us see if we apply the voltage across this specimen. Left hand side is positive and right hand side is negative for the specimen as shown in the figure. Then again, holes are attracted towards the negative potential and electrons are attracted towards the positive potential. Since more number of holes are present in p-type semiconductor, the hole current is larger. Whereas less number of electrons are there in p-type semiconductor since they are minority electrons generated due to thermal breakage of the covalent bond, their current contribution is less. But still, we can say that in semiconductor, total current is a summation of two currents, hole current and electron current. Electron current is normally denoted by IE and hole current is denoted by IH. So total current I in the semiconductor specimen is then summation of IE plus IH. In this simplified figure, again we have only shown the free particles. So you will see in P type of semiconductor, major number of particles, those are holes, and less number of particles, those are electrons. So holes are in majority and electrons in minority. And therefore, we are approximately saying that the current flowing through P type of semiconductor is because of holes, because electrons in majority. The current flows in N type and P type of semiconductor two mechanisms. One is called drift and diffuse. Second is diffusion. Drift is due to externally applied potential and diffusion is because of the density gradient exists in the material. Now we have already seen the drift current. When we apply the external field, due to external field, there is force acting on the particle and therefore these particles are moving to the appropriate either positive terminal or negative terminal depending on whether it is hole or electron. Whereas in the diffusion process, we are not applying any external potential, but since while doping, if the doping density is not uniform in the material, Then there is a density gradient created in the material as shown. Wherever there is a larger density, the particle tries to move from larger density area to lower density area. And due to this motion of the particle, due to energy difference, potential energy difference, the current will be flowing. In P type of material, the particle density tries to be coming at equilibrium, and therefore the movement of the holes constitute the current, and that is called hole current, diffusion hole current. Whereas in N type of semiconductor, if the particle moves due to the density gradient, those are electrons from high density to the low density area movement. This process is called as electron diffusion in the N type of semiconductor. And due to movement of this electron, the current flows, that is called as diffusion current or diffusion electron current. So therefore, total current in the semiconductor is because of drift as well as diffusion. This diffusion process will be stopped automatically when the density equilibrium is reached in the semiconductor. Now let us see the construction of p-n junction. Up till now we have seen the intrinsic and extrinsic semiconductor. Now you can make the use of p-type and n-type material to make a p-n junction. By joining together the semiconductor p-type and n-type with the process of fabrication of the semiconductor, we make a p-n junction. Now here in the figure, p-type material is shown and n-type material is shown, and they are joined by a semiconductor fabrication process. They forms a junction. So we will see in p-type material, there are free holes with their corresponding immobile negative ions. Whereas on n-type of side, there are free electrons with its positive immobile ion. Here in p-type material, the holes are in majority, whereas on n side, the electrons are majority. Whereas here also indicates some of the covalent bonds are broken due to thermal energy. Therefore, on n-type material, we will see this electron generated by thermal energy that adds to the majority electrons, and this hole, since it is very less in amount, therefore they are constitute the minority charge carrier. Whereas in p side also, this thermally generated electron hole pair, the holes are contributed to majority charge carriers, and very few electrons generated remains behind, those are constitute the minority. So in p-type material, electrons are the minority. The electrons are shown here by the solid dots and holes are shown by the hollow circle. Now let us study the operation of a p-n junction under no external electric field. Here in the figure now, we have shown on p side the majority holes, on n side the majority electrons, and we silently drop the minority particles and the immobile ions. Now, due to density gradient, here on p side there is large density of positive charge particles, and on n side there is large density of negative particles, and therefore due to density gradient the electrons are moving from n side to p side and crossing the junction. Whenever electrons are moving, if one electron moves from the material from n side to p side, it leaves behind the positive ion on N side. Whereas when one hole is vanished off on P side, means the additional electron is combined with the hole, and this additional electrons gives rise to a negative immobile ion on P side. So therefore, we will see here in the second figure, therefore you will see here on P side, A, B, C are converted to negative ions, and on N side, since one electron is lost, 1, 2, 3 atoms are getting converted to positive ions. So around the junction, there is a formation of positive immobile ion on N side and negative immobile ions on P side. Since these are the immobile ions, they are not taking part in the conduction. Whenever equilibrium is reached, the charged particle diffusion will be stopped. The positive immobile ions on N side and negative immobile ions on P side. And since they are not movable charges, they are depleted with the charge particles. Means in this area, you will not see any free charge particle. And therefore, this area is also called as depletion region. The process of diffusion will be stopped when the field created by the depletion region counterbalance the density gradient field. And this happens at a depletion potential of zero point 0.6 volt in silicon and zero point 0.3 volt in germanium. And this potential is also called as barrier potential or junction potential, also called as cut-in voltage of a PN junction. A PN junction diode is shown in the figure now with a simplified structure, a p-type material, n-type material with the two metallic electrode connected at the two ends. P-type material constitute the anode and n-type material constitute the cathode. The symbol of p-n junction is shown here. The direction of this arrowhead indicates the flow of current in p-n junction, and it indicates that current is always flowing from anode to cathode. There is no possibility of current flow from cathode to anode, and therefore we can say that PN junction is a unidirectional device. Now if we apply the external voltage to a PN junction, depending on the polarity of externally applied voltage, the behavior of a PN junction can be considered as forward bias PN junction and reverse bias PN junction. Application of a potential with respect to anode and cathode is called biasing of the PN junction. Now, if we make anode positive with respect to cathode, it is called forward biasing of the PN junction. If we make anode negative with respect to cathode, then it is called reverse biasing of the PN junction. Now, let us consider the forward bias operation. Now, in this figure, you will see on p-type side there are majority of holes, and here on n-type of side there are majority of electron, and we applied the battery positive terminal to p material and battery negative to n material, and therefore this biasing is called forward biasing. Due to this applied potential, the holes from p-type area are attracted towards the negative terminal of the battery, and therefore they crosses the junction, right, leaving behind the negative ions on p side around the junction, whereas the electron from n side, they are attracted towards the positive terminal, leaving behind the immobile positive ions on n side around the junction. So there is an accumulation of positive immobile charges and negative immobile charges around the junction. Since these are not movable, they are not moving under the applied external potential, and therefore this area is having charges positive on n side and negative on p side, but they are not contribute to electron flow or current flow, and therefore this area is depleted with the charge particle, and therefore this area is also called the depletion region, which exists around the junction. Here, whenever we increase the external forward biasing potential, more and more electrons are crossing the junction from n side to p side, and more hole crossing from p side to n side. And therefore, while crossing, they will combine with this immobile opposite polarity of ion, and therefore further reduces the number of immobile ions and constitute the larger current, which is governed by the external applied potential. So if we go on increasing the external potential, the current through the specimen is increased. That happens in the forward bias. Now let us study the operation in reverse bias. See here again, there is P side and there is N side shown with free electron shown by the plus sign, and immobile ions are shown by the solid dots with the negative sign. Whereas on N side, the minus sign indicates the free electron and the plus sign in the circle indicates the immobile ion. Now, when we apply the reverse voltage, means positive terminal of the battery is connected to N type of material and negative terminal is connected to P type material. What will happen? These electrons from N side are now getting attracted towards the positive terminal. So, electrons are moving away from the junction, and therefore, when this electron moves, they uncover one of the positive ion near the hole as shown here. Whenever voltage is increased, more and more atoms are uncovered and becomes the positive immobile ions near the junction. Whereas on P side also, when holes are attracted towards the negative potential, they uncover the immobile negative ions around the junction. And these immobile positive and negative ions, they form a depletion region. So if we go on increasing the reverse bias, the width of the depletion region is increasing. Here it is shown in the figure. Since the particle motion is less or very few amount of charged particles are now crossing the junction, the current constitute in the reverse bias is very, very small in the range of fraction of nanoampere called the leakage current. Whereas no majority charge carrier are crossing from any side to other side. Whereas the minority charge can carriers on both the side will not be affected and they can easily cross the depletion region. In fact, they are getting accelerated due to the external applied reverse bias. But since they are minority in nature, the current formed by them, that is the reverse saturation current denoted here as IS, is very, very small. Therefore, ideally speaking, in reverse bias, the current flowing through the reverse bias device is zero. Practically, very small amount of current flows. For all practical applications, we will consider this reverse saturation current equal to zero. If we apply the excessively large voltage across any practical PN junction, then due to large field, there is a lot of pressure or force applied across the charged particle and they are getting accelerated They acquire the velocity and they liberate the additional electron when they collides with the immobile ions. And large number of charged particles are generated, and this process is called as avalanche breakdown. And therefore suddenly large current flows after a specific large voltage called as reverse breakdown voltage. And therefore this very large current is damaging to the device if not controlled, and therefore it is avoided to operate the device above the breakdown voltage rating of a specific practical diode. The reverse breakdown in PN junction is classified under two broad operational categories. One is called Zener breakdown and another is called avalanche breakdown. In avalanche breakdown, due to excessive applied force by the external field, the charged particles are accelerated and they acquire the kinetic energy. When they move, they will strike on the immobile ion present in the path and give the energy to these immobile ions. Due to that, the electrons in this immobile ion shifted in the conduction band and available additional electrons or holes are available for conduction. Therefore, striking of the immobile ion by one electron generates additional electron, means two electrons are generated. When these two electrons again accelerated and strike the another immobile ion, they will liberate additional electrons and hole pairs. And therefore, suddenly large amount of current flows due to avalanche multiplication. This phenomena is called as avalanche breakdown. Whereas in certain diode with high doping density, due to high doping density, there are large number of charged particles available. And these charged particles are very loosely tied with the nucleus of their atoms. Whenever we apply the external field, this external electric field itself exert the force to snatch out the electrons from this shifted majority carrier level, and the particles are moved from this level to the conduction band due to the strong force of electric field only, and current will be suddenly increased. This mechanism is called Zener breakdown that happens due to application of the voltage, reverse voltage, as well as high doping density present in a particular type of diode called Zener breakdown, and the diode is called as Zener diode. The following figure indicate the volt ampere characteristic called VI characteristic of the PN junction. Here, the characteristics for germanium devices and silicon devices both are shown in the same figure. Consider the silicon device characteristic. In forward bias region, that is the first quadrant, the forward voltage is on x-axis and forward current is on y-axis. And you will see that up to the certain potential, say around zero point 0.6 volt, the current flowing to the device is 0. Actually, in practice, this current is very, very small, and that is due to the minority charge carriers. After 0.6 volt, if we increase the voltage further by fraction of volt even from zero point 0.6 to zero point 0.7, the current is rapidly increasing. And this current increase is governed by the identity ID is equal to I0 into e raised to Vf by eta Vt minus 1. This identity is called as the Shockley relationship given by William Shockley. It indicates that the current through the diode, that is forward current through the diode, is a function of applied forward voltage, but it is a exponentially related function. Whereas I0 in the expression is a reverse leakage current, whereas Vt is volt equivalent of temperature, and eta is a constant depending on germanium or silicon. Eta is 1 for germanium and 2 for silicon. Whereas Vt is equal to kT upon Q, where K is Boltzmann's constant, T is a temperature, and Q is a charge on electron, where Vt is also called as volt equivalent of temperature, and temperature T is in degree centigrade. So Vt is approximately T upon 11600, where T is given in Kelvin. So similarly, if we consider the germanium device, up to zero point 0.2 volt of cut-in voltage, the current is very, very small, and then it is rapidly increasing with the forward voltage applied. Again, the governing characteristic is a Shockley relationship. Whereas in reverse bias, if we consider the silicon device, when we apply the reverse bias, that is anode is negative with respect to cathode, no current ideally flows. Whereas in all practical devices, we know that there are thermally generated minority charge particles, and they are not affected by the external applied reverse bias. Rather, due to reverse bias, they are accelerated, and therefore very small current is flowing due to these minority charge carriers, and that is shown in this figure as IO, that is in nanoampere. Same case of germanium is shown, but germanium is more sensitive to temperature. So more covalent bonds are broken at room temperature, and therefore more minority charge carriers are present in germanium, and therefore the reverse leakage current due to minority charge carrier is more in germanium compared to silicon. That is shown here. When we apply the voltage in the reverse direction, which exceeds a certain potential for the practical diode, that is called the reverse breakdown voltage, then due to avalanche process or Zener breakdown process, suddenly the large current is flowing through the device as shown by the standing line in the characteristics. Now, during this portion of the characteristic, you will see that current is high as well as the voltage is also high across the device, and therefore power loss across the device is very high under breakdown condition. If the diode is not designed to bear this power loss, then it will be damaged due to excessive heat, and therefore it is avoided to be used the diode in the reverse breakdown region. Only special diodes like Avalanche diode and Zener diode, they are suitably designed to operate and bear with this reverse power dissipation, and they can able to survive in the breakdown region also, and therefore they are specially developed to operate in the breakdown region. And we observe that in breakdown region, the voltage across such avalanche or Zener diode are mostly constant here, right? Current is increasing or decreasing, but the voltage remains fairly constant. And this happens after the breakdown voltage called VBR, or reverse breakdown voltage, also called as peak inverse voltage for the PN junction. Now let us study the application of diode. The diode can be behaving like a mechanical switch. We can rather say that diode can be a electronic switch. Like in mechanical switch, when switch is closed and when the potential is applied across the switch, the current is flowing from the positive terminal to negative terminal of the switch. Whereas In diode also, when anode is positive with respect to cathode, that is in forward bias, this diode conducts the current, whereas when reverse bias is applied, the diode acts as open circuit and therefore no current flows through. That is similar to a switch which is acting as open circuit. Whereas during forward bias, since the current flows from anode to cathode, it is acting like a closed switch. Only difference is that in mechanical switches, whenever voltage applied across it and switch is closed, the voltage drop across the switch will be zero and current will be maximum. Whereas comparing it with the forward bias diode, the voltage applied across the diode to make it on will be always greater than the cut-in voltage, that is zero point 0.6 to zero point 0.7 volt. Therefore, diode is considered as an on switch with forward voltage drop across it around zero point 0.6 volt in case of germanium and zero point 0.2 volt to zero point 0.3 volt in case of silicon. Whereas during reverse bias case, when the switch is open in the mechanical switch, no current flows through the open circuit switch. Whereas when reverse bias is applied across the diode, and if you compare diode with this open circuit switch, the diode is in reverse bias, which carries no current ideally, but practically the current flowing through the diode, that is the reverse leakage current, which is very small, but not zero. Therefore, ideal mechanical switch have zero current when open circuited, whereas practical diode in the reverse bias is carrying very small amount of current near to zero, that is in nanoampere, and therefore diode can be used approximately as open circuit in reverse bias. The characteristic of a switch is shown here in the figure. So today, that's all friends. We will see the DC power supplies in the next lecture. Till then, bye bye. Have a good day.